button.
So
let's do it. All right, I think the live stream has kicked off. I'll post in the live chat to see if someone can confirm that we're live. It says one concurrent viewer, and that's probably me. Oh, hey, Aaron, what's up? Great. We will start promptly. Thanks, Aaron, for chiming in. Hello, everyone. We're doing a live stream. It's been a while. It's been a while since we talked about WebAssembly. But for those of you who are live, welcome. For those of you who are tuning in from different time zones, we appreciate you showing up. If it's early or late, actually, one of our speakers is calling it at 3 a.m. So thank you for everyone around the world and WASM enthusiasts. For those of you who don't know what this is or watching the recording later, this is the WebAssembly San Francisco meetup, WASM SF. We used to do this in person every month in San Francisco. Now we're doing it occasionally online for folks around the world. And in fact, both speakers today are not based out of San Francisco. So it's definitely an international kind of day. Before we get too far along, some housekeepings. We have a code of conduct. It's on our meetup page. And in summary, be excellent, be awesome to each other. If there's any contact issues, you can hit me up on Discord, the community Discord, which I'll talk about in a minute, or let me know through Twitter, through our WebAssembly SF Twitter handle or other means. So I mentioned Discord. We're trying a new thing. We're using Zoom for the speakers and YouTube Live like we've done in the past, but we're trying out Discord for the networking social parts of it. So between the talks and after the talks, we'll all head over to the community Discord. If you don't have a link to the community Discord, it's on the meetup page, as well as the WebAssembly Summit page and other places around the internet. And actually, if someone can, I'll post that link in the chat in a minute on the YouTube Live. So this is new, it's experimental. The code of conduct applies as well over there too, especially since we'll be using audio. And the WebAssembly community Discord also has a code of conduct, so please be respectful. And we'll see how it goes. Without further ado, I want to give an intro of our two talks. We actually have two very different talks. One is about runtimes and implementing WebAssembly in the cloud, and the other one is languages. And so it's gonna be a good, meaty technical discussion today. So hope you brought your thinking caps on and ready to learn about some new cool tech. And taking it off, I'll turn it over to Connor, who will be talking about Suborbital and all the things he's been building around WebAssembly in the cloud. And with that, I will say, take it away.
All right, thanks, Jonathan. Yeah, so my name's Connor. I build the Suborbital Project, which is a group of open source tools and frameworks and runtimes that allow you to use WebAssembly and make it useful in server-side contexts. And so I'm going to talk today about specifically the Atmo project, because that is kind of the flagship. It's the main one. And I'll give a demo. I'll give a little bit of information about how it's built, the architecture, and some of the design patterns and reasoning behind it. And then hopefully there will be time for some questions at the end. So I will throw this up and we can get started. Hopefully I can maybe get a verification from Jonathan that you can see my screen.
I can see it.
All right, great. So yeah, let's jump right into it. So Suborbital, I kind of already touched on it, but it is, it is a collection of projects, but the overall goal of Suborbital is that server-side WebAssembly, endpoint, which is making it really easy to build, run, and actually develop applications for the server that are powered by WebAssembly. And it might be, a little bit weird to say this, but actually, I'm hoping that WebAssembly will become kind of an implementation detail. I'm hoping that, in a couple of years from now, WebAssembly is not going to be the headline feature, but rather just something under the hood. And it's going to become so commonplace that you won't even really care that WebAssembly is powering it. So the projects under the umbrella are kind of shown here. The three on the left, Reactor, Grav, and Vector, are what I call the building blocks, and they are individual components that, when you put them together, form Atmo. So Reactor is a job scheduler or a function scheduler, and this is actually where most of the WebAssembly magic happens. This is where we schedule WebAssembly modules, we manage their inputs and outputs, manage their memory, we load them and unload them from the disk, all sorts of things like that. And then Grav is a decentralized message bus. So it is actually an abstraction over any kind of discovery and transport mechanisms that you might want to build your application on top of. It allows you to write asynchronous messaging and swap out transport and discovery plugins without needing to rewrite any of your code. And then Vector is an HTTP framework for Go. Not exactly important when talking about WebAssembly, but it is kind of the first line of defense. It encodes a lot of security best practices and performance best practices to make sure that you are building a performant web server. And then, like I said, Atmo kind of puts all of this together. It allows you to run a scalable WebAssembly powered server side system. It can scale, it can mesh together, communicate with a group of instances, and it kind of gives you the best of all these three while having a pretty unique development system. And Atmo has been developed alongside what I call the SUFA design pattern. And this is something that I've been working out to help me guide the actual development of Atmo itself and the development of the directive concept that I'll talk about in a minute. So SUFA stands for Simple Unified Function-Based Applications. And I think it's fairly straightforward, but I want to touch on each of those points in particular. So simple means that it is simple to both understand and simple to run. So, developing Atmo applications should be simple, and actually orchestrating and running and maintaining Atmo applications in a production environment should also be quite simple. You don't need a complex network topology. You don't need, all sorts of, services that your cloud provider gives and all the bells and whistles. Just an auto scaling group is more than enough to run Atmo, and it shouldn't get more complicated than that. And then unified means that when you build your Atmo application, you are, it results in one singular thing. It is one deployable unit. It is one thing that needs to get deployed to the cloud or deployed to your environment. You don't have to build, dozens or hundreds of Docker images for all of your different microservices. It's meant to be entire project built into one unified deployable that Atmo then intelligently uses to build a scalable system in the cloud. And then function-based simply means that your application is comprised of, small, easy to build functions that are independent from one another and that basically take input, provide output, and we'll see how you fit those functions together to form an application in just a second. So I don't think I need to really answer this question for a WebAssembly meetup, but I think it's important to touch on, especially for if you're new to WebAssembly or if you haven't seen it in a server-side context before. Why would we choose WebAssembly to build our server-side applications, and why did I choose WebAssembly to build Atmo and Suborbital on top of? And it comes down to these three things: portable, secure, and fast. WebAssembly is portable, meaning that it can run on all sorts of different processor architectures, any device types. You can run it on ARM, you can run it on x86, you can run it on the edge, central cloud, whatever you want. It is very flexible. It is secure because WebAssembly is based on a sandboxing model that is denied by default, meaning that in order to grant code running inside of a WebAssembly sandbox access to things, it has to be explicitly granted to that module. You do not get anything necessarily for free, and that means that your code is very secure. And when you run that code, your environment is very secure, especially, for example, when executing third-party or untrusted code. you know that code can't do any hijinks because you have to explicitly grant it access to things. It can't just run rampant on your network or your file system. And then finally, it is fast. We've seen a lot of benchmarks lately. If you look in the WASM Discord, or if you look on Twitter, there's been a fair amount of benchmarking happening lately, and it's pretty impressive. And there's been a fair amount of improvement. There are a bunch of different ways to build and compile and execute WebAssembly. There's ahead of time, there's just in time, there's all sorts of different strategies. But at the end of the day, what you're getting is something that is quite performant. And I think we're going to be seeing plenty more improvement in this area as we go forward. So the goal with Atmo is you write functions and compose them to form your business logic. And then you create what we call the directive. And then Atmo uses the directive to run your application and figure it out. It shouldn't be up to you, the developer, to dictate exactly how the application is run. Atmo is designed to be a little bit more intelligent and run the application in a way that it is best for the environment that it's in. And I'll talk a little bit about that at the very end. So this directive that I've been talking about, it is the way that you compose these functions together to form an application that can serve your business needs. And you do so with it's a declarative format called the directive. It's a YAML file, and it lets you describe everything about your application that Atmo would need to execute it properly. So you can see things like, API endpoints are being defined, and a set of steps are given to, handle requests to that API endpoint. And so you can see, the ability to call functions, the ability to have iterators that allow you to do lots of really great, loops and conditionals, and, the ability to run concurrent jobs, and the ability to do things like, set environments specifically for each function. And there's a bunch of other powers that this has, like error handling, and I'll kind of get into that a little bit later in the demo. But the main takeaway and the main reason why Atmo is designed around this declarative format is that it allows you as the developer to care about what is being run, and you let Atmo figure out how to run it. And this will get more useful as Atmo and the suborbital ecosystem evolves to span different computing environments like central cloud and edge cloud, because Atmo will be able to intelligently decide where particular functions within your application should run, and determine, should something run on the edge, should something run in the central cloud. And because you've designed your application with a declarative format, you don't need to rewrite anything. You don't even need to know which functions are running where. As long as Atmo executes your steps as described, let Atmo decide what is, the most efficient way to run your code. So I'll do a quick peek into Atmos architecture internally. I mentioned before that Reactor, Grav, and Vector are the building blocks, and they truly are building blocks towards creating Atmo, because all three of them are well represented within Atmos internals. So it all starts when network requests come into an Atmos server. They're handled by an instance of the vector server, what we call VK. And VK does all of the handling of TLS. It does all the routing, and it does all sorts of logging and ensuring that your application is being handled with the best performance possible. And it hands individual requests off to what's called the Atmo Coordinator. And the coordinator is kind of the brains of Atmo. It's the glue that kind of sticks these three building blocks together. And it is the thing that is reading your directive and instructing the system as a whole to execute the functions of your application in the right order, and handle the what should be input into certain functions and what to do with the outputs of those functions. And it does that by communicating over the Grav mesh, or the Grav bus. And it's important to note that, because Grav is the intermediary for all function calls within Atmo, it means that the function being called by the coordinator doesn't necessarily have to be right on the actual instance of Atmo where the request is received. Because Grav can be networked and can mesh together many instances, the function being called might actually be on a different box, or it might be, in a different VPC even. And so by executing function calls over this message bus, it allows us to, be intelligent and distribute these functions across many instances if needed. And Atmo can intelligently load and unload functions from its internal scheduler to make room or to be more efficient when needed. And all of that execution is done within an instance of the Reactor Scheduler. So, whether the message to execute a function is coming from internally within the instance itself or coming over the network from another instance, that message is received by Reactor, and Reactor will actually run the WebAssembly module associated with the function, and it will ensure that the correct input is given, and it will then send the output back as a response message, which will then be received by the Atmo Coordinator that originated the request. And so this gives us a really flexible platform to build applications on top of, and it especially shows why the declarative nature of the directive is important, because it allows Atmo to make those decisions of, do I mesh to a different instance that has the function already loaded, or do I try to load that function myself and put it into memory and execute it myself? Atmo can kind of do those decisions as needed. So I think that's enough talking. I'm going to give you a bit of a demo. So I've got an application here called Telescope. It's actually open source. So if you head over to my GitHub, Cohix, and you can find the Telescope repo if you want to follow along. And it all centers around that directive file. So that's always going to be the entry point for an Atmo application. It includes a little bit of metadata, like what version of Atmo are we using, for example. And then it describes all of the handlers of the application. So there's a couple of different ones here, and I'll go into some of them in more detail. But at a high level, we have an endpoint for getting some files. We have an endpoint for listing some repos. We have endpoint for getting a particular repo, and then we have this one at the bottom, which is for creating a report. And I'm going to talk about this one a little bit later. But we'll start with this list repos endpoint, because it's fairly straightforward, and I want to walk through how the directive interacts with the various functions in your application. So you can see that we're handling something that looks like a request, and it's coming to this endpoint, and it's got this HTTP method. Okay, fair enough. That's pretty straightforward. And then in the steps to handle this endpoint, we are calling a function, and this function is called list repos. So let's go check that out. This one is written in Rust, but Atmo and the suborbital projects do support multiple languages. You can use Rust, you can use Swift, and assembly script is coming like within days. I have most of that completed, and assembly script will be up in public probably with Atmo beta 3, which will be coming pretty soon. So each of these things in the project are functions, and they encapsulate a particular piece of business logic. So the list repos function in particular, it's designed to fetch a list of the repositories within a particular GitHub organization. And in order to do that, we actually can use what is called the Suborbital Runnable Api, which is a set of capabilities that have been granted to the functions in an Atmo application by means of this runnable library. So there's a library for each of the supported languages that gives you access to these capabilities. So I'm going to talk about a bunch of these, but just as you can see here, like these are some of the things that are available to you: accessing a cache, reading files, making HTTP requests, and more. So we're going to use that right off the bat, and we're going to use this file capability to get a static file. And that's actually one of the features of Atmo, is the ability to bundle static files with your application. And so when I build the Atmo application, that unified deployable that I talked about earlier, the form that it takes for Atmo is what's called a runnable bundle. And this is a zip file that contains everything Atmo needs to run your application. You can see it here in the project. It gets built along with everything else. And so, all of the WebAssembly modules that get compiled from your functions, all of your static files that you want to bundle and your directives all get put into this runnable bundle, which Atmo then reads to actually run your application. So we use that get static function from the file capability to read this organization file, which tells us which GitHub org it is we're dealing with here. And then it uses the HTTP capability to make a request to the GitHub API to then actually get information about the repos in the organization in question. And then we do some JSON work, nothing fancy. And then what we're actually going to do is, for each of those repositories that we get back, we're actually going to cache them. So we're going to use Atmos cache capability to store details of these repos for use later. And we can do things like set TTL. And this cache is something that's configurable. So when you're running a dev server, it'll be an in-memory cache, but you can connect it to things like Redis or whatever you want to do. So then we respond with JSON and call it a day. We can do things like setting content type and headers and all that fun HTTP stuff. So let's we'll take a pause and we'll actually build this thing and give it a try. So Suborbital has a CLI tool. It's called Subo. And if I run subo build, I'm going to pass dot for the current repository. And I'm actually going to pass a flag called native that instructs Subo to use my machine's native toolchains. So the actual Rust, Cargo, and Swift compilers that are installed on my machine. By default, Subo actually ships with a Docker-based toolchain. So you don't actually need to install any of the toolchains or any of the CLIs and the various Rust targets and all the different things to build WebAssembly. Subo will actually do that for you. As long as you have Docker installed, it will kind of figure out how to do that for you. So as soon as I hit that, it's going to compile each of the functions in my project. It's going to add all the static files to my bundle. I'm going to make this font a little bit bigger just in case. It's going to add all of those static files to the output bundle. And then this zip will contain everything that Atmo needs. And I'm going to start up an Atmo dev server by running sudo dev. And this is going to actually read that bundle and create my application. So Atmo starts up and it serves on 8080. So why don't we go and pop open an HTTP client and we can take a look. Postman always takes a second. Here it is. Okay. So we will start by calling that repos endpoint. You'll remember that that was defined here in the directive with the get method. So if I make a call to that, we will get a response with all of the different repositories from the suborbital organization, which is really cool. Now, you remembered me say that we cache the details of each of these repos, and I want to show that that's actually working. So you'll see here, it took about a little under 300 milliseconds to get this all back. We were doing a network hop to the GitHub API, had to do TLS, all that kind of stuff. So yeah, it's not the fastest. But if I go over here and I actually make a request for a specific repo, if I ask for just the Atmo details of the Atmo repo, you'll see that I get that response back in just a couple of milliseconds because Atmo is actually reading that from the cache. So why don't we go take a look and see what that's all about. So if we go to the get repo function, this one is for, like I said, getting a particular repo. And it's doing some similar things. It's reading that file, the configuration file, to determine what organization it's mapped to, and then it's actually checking the cache right off the bat to see if the repo details are stored there. And if they're not, then it'll go to the GitHub API and it will fetch that repo, fresh, and then fill the cache back in behind it because it's a good citizen. But if it did actually find it, then cool, we have the JSON for that repo, so we'll just return it, no big deal. So this is a pretty good representation of how to use the runnable API and gain access to things you would commonly need to build a web service. But let's maybe get a little bit more complicated. So let's take a look at this report API here. So this endpoint actually has multiple steps involved and has a little bit of extra configuration. So first off, the point of this endpoint is to create a report of the stars on the repos in the organization that we're configured to connect to. And so, this is a post endpoint. We're going to hit the API v1 report endpoint, and we're going to execute a couple of different runnables or functions to handle this. So the first one is that list repos function that we saw up above. So you can kind of see that you can reuse functions among different endpoints and get some nice modularity there. And we're using a clause here called as, and I'll take a second to explain how the functions within a handler actually interact with each other. So when you're executing the steps to handle a request, Atmo is creating what's called the request state object. This is an ephemeral object that exists just for the lifetime of the request. And for each function that executes, its output gets stored into this state object. And it's essentially a dictionary, like a map of key value pairs. And so the list repos output gets stored into that object so that functions later down in the chain can actually access the information that was returned. And, list repos is a weird name to be accessing information from. So you can actually alias the value in the state object by using the as clause. So it's basically essentially run list repos and store it as repos in the state. And so that brings us to the second step in this handler, which is a for each operator. And for each allows you to iterate over an array and execute a function on each element of that array. So you can see here, we're actually going to take the JSON array that we got back from the list repos endpoint, which is an array of repositories, and we are going to execute the send report function on each element of that array. And we'll see how that works in just a second. So why don't we take a look at that send report function here? So, somewhat similarly, we're using the Runnable API to gain access to some capabilities, but this one's a little bit different because we are using the request capability to actually access that state that I talked about a second ago. And we're accessing a special key called LM, which is what gets set when using an iterator. So when the send report function is executed, it's being executed on one element of the array stored in the repos value. And in order to get the value of that element, we ask Atmo, please give me the LM that I am being executed on. And so we do some similar things here. We do, the JSON dance to unmarshal that into a repo object. And we're going to filter out repos with less than 5 stars because, no need to create a report about those. And then we are going to use that same file capability with the get static to fetch a different configuration file here called webhook that I'm not going to show you because I don't want you to spam my Discord channel, but it's going to read a Discord webhook URL from that file and then build a webhook payload and send that webhook to Discord. So you can see you can do all sorts of things like setting headers on those requests and setting the body and all sorts of standard stuff that you would expect from an HTTP client. So to summarize, we're going to get a list of the repos in the suborbital organization, and then for each of the repos in that list, we're going to send a report only if there's more than 5 stars. So we'll give that a try. I've got the configured Discord channel here. It's called reports within the suborbital Discord. If you want to join, just go to chat.discord.dev and that'll bring you right to the Discord channel. So let's hit that report endpoint, the API v1 report with a post request, and we'll see what happens. So I'll quickly go over here and show you that the output of the Atmo instance is running here, and it's showing you stuff like API v1 report completed with 200, etc. And we can see that the response of this post request was the same as the list repos because we're just passing that along to the caller. But then we pop back over to this Discord channel and we can see that we got information about the repos under suborbital with more than 5 stars, which is pretty neat. So this is all great. We built an API. That API has some pretty cool endpoints. and we can build and reuse functions, compose those functions together to form the business logic of our application. But I do have one more little tidbit to go on the end of this. I'm going to kill this Atmo server for just a second, and I'm going to run a different build command. And I'm not going to spoil it, but Telescope is actually a full stack WebAssembly app. And well, what does that mean? So I've just built an extra component to this application, and I'm going to restart that dev server just so that we can maybe give it a try. And you know, if you look at the Telescope repo, it directs you to this particular URL. So why don't we hit that? Okay, well, we're getting a web version of the information about you know, the repos in the suborbital organization. So this is kind of cool, but you know, what's special about it? Well, the answer is that this is actually a front-end application built using WebAssembly. So if you look here, the application is built in Rust, and it uses the U framework to actually manipulate the DOM and build you know, a single page application. So if you look inside of this app directory within the static part of the application, you can see that the make command that I ran took that U application and built it into an HTML page with some CSS and a WebAssembly module that is being served by Atmo from this static bundle to the browser. And then the front end compiled to WebAssembly is interacting with the backend compiled to WebAssembly. So essentially, this is a full stack WebAssembly application where the front end and the back end are both entirely built using WebAssembly. I'll give you a very quick tour of the web app, and then we will call it a day. So we'll take a look first at the main.rs. So this is kind of like the index of the application. You know, we're setting up a component. You know, the component is called homepage. It has various, you know, lifecycle methods like create and rendered and updated, and etc. And then a view method, which actually does rendering of some HTML. So we are, you know, creating various elements, and then we are using the U frameworks APIs to actually iterate over some Rust structs to create the list. And you know, the information is being fetched from this API function called get repos. And this is actually making a fetch request, like a browser API fetch request to that, you know, backend service. And then the result is being put into this model repo struct that you can see here. And if you take a look, model is actually living over here on its own. It's you know, the repo struct is not specific to the front end to the back end. And if we look at the list repos function once again, we will actually see that when we are unmarshalling the JSON that we get back from the GitHub API, we're using that exact same model repo struct. So we're actually sharing code between the front end and back end, compiling them both to WebAssembly, and then running them both in the browser and on the back end using U on the front end and Atmo on the back end. So that's the whole entirety of what I have to show. I'll switch back over the slides real quick and just say thank you. That's the end of what I want to show. You can head over to suborbital.dev to get all the information about Suborbital's projects, and visit the GitHub repo as well. You know, give Atmo a look, try it out, clone it, run the Subo CLI tool, give all the feedback that you can. And you can follow me at Cohix on Twitter, and Suborbital is Suborbital Dev on Twitter as well. So that's it for me. Let's maybe see if there's any questions.
Awesome. Yeah. So folks who are in the live stream, feel free to use the live chat on YouTube. I didn't see any questions. I saw some excitement, some pseudo/subo typo jokes, and that's that's it so far. Yeah, we have plenty of time, but so feel free to hop in. Aaron says, "Thank you, great talk."
Very welcome. And you know, I'll reiterate and say that I love people trying things out. I love getting, you know, all the feedback. Feel free to open issues. There are GitHub discussions available in the meta repo. You can also join the Suborbital Discord, or you can ping me in the WebAssembly community Discord at Cohix, pretty much everywhere.
Nice. Oh, we'll give people some time to ask the questions. We're just getting a lot of praises and claps. Maybe we'll wait. Is there a story behind the name Suborbital?
I'm a huge spaceflight nerd. I guess that's really all there is to it. And it was available on GitHub. It's always hard to find good names available on GitHub and Twitter and stuff like that. So it was just a happy coincidence. Yeah, all of the projects have a bit of a space flight, sci-fi theme to them. Kind of keeps things cohesive, and I like the feel of it.
Awesome. Let's see, any other? Maybe I'll just throw one out there. With the full stack WebAssembly demo, you had Vue for the front end, and obviously the entire Suborbital on the back end. Do you think you'll be able to have that same capability across other languages, like Go in the browser or AssemblyScript?
Yeah, absolutely. There's nothing stopping you from mixing and matching languages, both in the front end and the back end. I know there's frameworks for Go in the browser, and AssemblyScript can do some things as well. So if you want to mix and match, there's absolutely nothing to say you can't. All it really is the files being bundled into the static directory, and then Atmos serves them. And so whatever you put in there, no big deal. Doesn't even have to be WebAssembly, but this one, for dramatic sake, decided to make it full stack WebAssembly. Cool. So it can be whatever you want.
Awesome. And you mentioned AssemblyScript stays away. Is there a roadmap for features, new languages? Where would people find that?
Yeah. So I'm actually working on publishing a roadmap. I have a draft of it right now. I do think it's really important to tell people where the project is going. But the short version is my focus right now is on language support and more capabilities. So AssemblyScript is coming very shortly. Go via the TinyGo project will come very shortly after that. And then adding new capabilities such as being able to access databases via GraphQL, being able to access blob storage like S3. These are all the kind of capabilities that I want to be adding in the near term to just make building web services on the Atmo platform a little bit easier.
Awesome. We are getting more praises. Fans of AssemblyScript. Josh was a former presenter on our AssemblyScript day, so he's got hype for AssemblyScript. I'm not seeing any questions coming in, which is a good thing. This means people are probably either heading over Discord or looking at the repo. So maybe with that, we'll call it a little bit early before we get to our next section. So virtual round of applause for Connor and Suborbital. I'm trying to see. Yeah, there's a Zoom clapping emoji. I don't know if that came out in the live stream. Anywho, before we move on to the experimental Discord audio session, we do have a question. I want to pause and read that question real quick.
Sure.
From Joseph JJ. What are the biggest issues you are seeing in job scheduling complexity of WASM processes? Are there similar levels of complexity, for example, with pods and Kates?
Yeah, complexity is definitely a concern. Like I mentioned to you before we started the show, but I just got a new laptop and I was setting up, the various environments and whatnot on there. And honestly, the number of tools that you have to install to, get the tool chain all set up correctly, unless you're using Subo, is quite high. Like you have to install 5 or 6 different things and configure things correctly to get everything compiling properly. And then when it actually comes to executing that WebAssembly, there's glue code that is needed in all environments, whether it's Atmo or whether it's in the browser. Luckily, tools like Vue and the trunk bundler and WASM bindgen and Subo and the suborbital tools generate a lot of that glue code for you. And so, most of the time you probably wouldn't even need to deal with or care about that. But it's definitely, a struggle for people getting started with it. That's why I built the Docker toolchain for Subo, is that you don't need to do any of that installation. And that's why, the directive is nice, because you can just declaratively say which functions to run and you don't have to imperatively interact with the WebAssembly runtime or whatever. So, I really hope that as we move forward, the amount of glue code needed is lowered because of things like WASI and more support and more ergonomic language bindings for the WebAssembly runtimes themselves. But it's improving all the time. It's definitely better than it was a year ago, and I assume it'll be better a year from now as well.
Awesome. And part of that question was around the scheduler, so more specifically, because Kubernetes is notorious for a very complicated, for good reason, scheduler, because these are complicated problems. Is there any difference or uniqueness about scheduling, let's say WASM workloads versus a container workload? Is it easier? Is it harder? Any thoughts on the scheduler?
Yeah. So it's a very different beast because, well, at least in the use cases that I've been using WebAssembly for, the execution is very short-lived, right? These functions are up and gone in milliseconds. And so the scheduler is designed around that. It's designed to be very high performance, high throughput. And so it doesn't have the same problems as the Kubernetes scheduler, which is designed to be like guaranteeing the state of a system for like long periods of time. And so different challenges, and things like the Crosslet project are actually integrating WebAssembly into the Kubernetes ecosystem, and it lets you actually take advantage of the Kubernetes APIs to run that. But in general, I think they're slightly different problems. There will be long-running WebAssembly, I'm sure, like absolutely. But especially for running web services, they don't necessarily have to be long-lived. And so the scheduler that I built, the Reactor Scheduler, is designed to kind of handle both of those cases. But in most applications, you provide an input, it starts the function up, it runs, it provides an output, and then it dies. And that can happen in single-digit milliseconds if you need it to.
Awesome. Cool. Well, that's a great question, and we'll wrap it there. So before we head over to Discord, I wanted to just do a quick plug for a community event. I forgot to mention at the beginning, the Linux Foundation is having their biannual KubeCon. KubeCon EU, I think, is this upcoming one on the beginning of May. And there's a dedicated sub-event or co-event called Cloud Native WASM Day, if I got that right. And actually,
That's
Connor
right.
will be presenting, and a bunch of other folks from the WebAssembly beyond the browser, in cloud native context, will be presenting there. So if you haven't heard about KubeCon, definitely go check it out and register for the Cloud Native WASM Day if you're interested. And with that, oh yeah, go ahead.
I was just going to say, Lynn Clark's giving a keynote that I'm really excited for, so definitely check that out, whether live if you're in the European time zone, or later if you're like me and that's like at 2 a.m.
Awesome. Yeah, time zones are fun. Well, we are going to go try our experiment. I'm going to pause the camera. I'll hop into Discord. We're all going to go into that WASM SF audio channel on Discord and see what happens. It's almost 5:45 PT. So at the top of the hour, we'll start with our next speaker. And if you're there, we'll chat there. If not, we'll see you on the internet.
Thanks, Jonathan.
All right, I think we're back to streaming. If someone on the live chat can just give me a thumbs up that they can see the live video, not the standby. We're still catching up on our end. Okay, I can see myself. I think we're good. I think we're good. Well, those of you who missed the Discord, that was fun. We had a good conversation about learning, about enterprise use cases. So we'll try that again after Mike's talk. But I'm super excited for Mike's talk. This is similar in vein of building software that can run on servers, but it's about languages. This is in particular one of the languages that they work on at Fluence. Also, huge kudos to Mike for staying up. I think it's 4 in the morning for him, maybe a little bit later at this point, but he wanted to give it live. So we're appreciative of getting you in real time. So extra special warm welcome from Webassembly SF, and I will let you take it from here.
Hi guys, thank you, Jonathan. So my name is Mike, and I'm doing engineering for Fluence Labs. And today I'm going to tell you about our Aqua stack. This Aqua stack includes several things, like Aqua language that Jonathan say about, also special intermediate representation that I will focus on, and also our runtime called Marine. And in particular, the agenda of my talk is as follows. So first of all, I will talk a little bit about Fluence, what we are doing and how. Then I will talk a lot about Marine runtime, and especially about concept of service. Then I will talk a little bit about our new language called Aquamarine, or Aqua, just Aqua. And then we will talk really a lot about Aquamarine intermediate representation and about how the internals of Aquamarine intermediate representation interpreter looks like. During my talk, I will dig into details of some on some site, and I will not cover also a lot of things in our Aqua stack. So please, if you have any questions or you don't understand some moments, or you have any other thoughts about this talk about our language and so on, so please ask me questions, or please write my email. It will be on the last slide. So I think we let's start with Fluence. So actually, Fluence is the thing that we call open application platform. So this open application platform includes several things. The first one is a peer-to-peer stack. So peer-to-peer stacks allows you to compose some APIs, APIs of microservices, yes, data, and so on. And also it's a way using some proprietary cloud stacks, the DNS, and so on. And also open application platform is a hosting marketplace with monetization. By monetization here, I mean that actually monetization isn't implemented now, but it's in the future and our future plans. And it's in future, we hope that developers will be get paid by the fact that their modules or services used by anyone in the Fluence network. And it's also called a licensing-based paid. And to allow all of this, yes, there is a special language called Aqua. Yes, this language is inspired by pCalculus. Actually, it isn't based directly on pCalculus, but many things internally inspired by it, and also by session times, maybe called such great calculus. And so Aqua internally is just a medium that allow you to coordinate and orchestrate network that consists of several peers with services. For example, on the right side of the slide, you could see a simple scheme with two clients. So clients here, and on all other slides is just a browser. Yes, it's just a client that works inside browser. Here you can see two clients, one Firefox, next one is the Chrome, and imagine that guy from Firefox want to send some data to like guy on Chrome, and with this data he want to do, I don't know, he want to compose some services, he want to call some services or some like combine some data and so on. And service actually is one of the most important concepts inside our Fluence. And this concept is important for other part of the talk. And let's consider it in more details. So actually, service here is a WebAssembly based like code. Yes, so sorry, it's code compiled to WebAssembly. That's why it's sandboxed. And also this service is composable with Aqua. Yes, I mean that Aqua could call service. I will show later how it should be. And also we are using WebAssembly interface types to make our service more user-friendly. I mean API of service more user-friendly. Also, services could be stateful or stateless. For example, they could have states in memory, or they could access file system databases through WASI. And also, they could be extendable with some external executables. For example, here you can see that like on the service, there is some external, the service like written on Rust, and for example, written on Rust and compiled to WebAssembly. Could call with special feature that I will show you later. Other services, for example, IPFS, or like I don't know, some database like MongoDB or something like this. So, and let's dig into services more in more details. An example of Marine runtime. Probably you have seen my previous talks about things called FC, and actually, Marine and FC is the same thing, are the same things, but like we renamed FC just several days ago. So that's why I will call FC next Marine. And on the slide, you could see how Fluence could be considered from like service-oriented point of view. There are several special terms on the slide. So the most important one is a module. Yes, so module is a WebAssembly module. So this code written on Rust, C++, assembly script, and compiled to WebAssembly with our special API. And several modules could be combined to entity code service. And in this turn, several services could be combined to entity code backend, or like, I don't know, like a super service. And here functions means that function written on Aqua, on our special language. And it's important that this function could compose any services that form the backend. And it's also important that each service could be located on different peers inside Fluence network. And also, for example, they could, of course, be on the one peer inside Marine runtime. And for users, they could be considered as just a function from just function as a service. So here, a function is a letter F from FAS. So as I already said, so service is a group of modules, and they link together by sharedness and linking scheme with scope of interface types. So I think you know a lot about WebAssembly internals, and here you know that each modules inside WebAssembly could have their own imports and their own exports. And interface types allows you to do sharedness and linking scheme. This linking scheme allows modules to keep their state in private. By their state, I mean memory, table, globals, and so on, and just to link with each other by imports and exports. So here you could see that three imaginable modules link together by linking corresponding imports and exports. On the slide, you could see example of Hello World written for Fluence. So it's about 6 lines of code. it shares the same scheme as a Webassembly engine. So here you can see one function called greeting. Yes, this function is wrapped by the procedure macro called FCE. And this FCE works similar to Webassembly engine macro. And here the important thing that you could operate by vanilla REST types, yes, by strings, vectors, records. By records, I mean strings, sorry, structures, and so on. Also, here we could see more complex example. So this is a service that like complete code could be found by the link. This service consists of 3 modules. So this service intended to, so it's like a test service or like a model service. It's intended just to like download by provided URL some, like, I don't know, some bytes, yes, by just running curl, and then save these bytes to some file name. So here you can see the main function of this main module is called site storage. And this function takes a URL and file name, and internally this module code 2 other modules called curl and local storage. And like from code point of view, from Rust code of point of view, it looks similar to FFI. Yes, you need to do like you need to define foreign section. Yes, wrap it with FC and all the same. Yes, and here inside the section you could use vanilla REST types with several restrictions. I will maybe so I won't tell a lot about this restriction, but if you want more details, please ask questions. And let's see more and more complex example. Here you can see that FC could be applied to a structure, as the structure contains some non-trivial types, like vectors of bytes. And here you can see that this this structure could be used inside foreign block. Yes, and here you can see that like it's a vector of vector and so on of reference to this like the structure. So well, the rules are the same, but so as far as I know, Webassembly engine doesn't allow to like use some internal vectors inside the vectors. Also, like it's important thing because we use share nothing linking scheme. So reference here means that like so here reference is meaningful because it allows you not to copy types by calling some wrapping function. But for example, imagine that reference inside export functions, it means nothing in terms of like memory, because copying would be done in any cases because it's shared nothing linking scheme, and we not have now shared memory between modules. So each module keeps their memory in private. But like it allows you to, for example, port easily some already existed software, existed code, just applying FC macro to the like some function that you want to make export or imports or import. And complete example of this like test. So actually, this tests and our tests you could find by this link. So there are more examples of more complex functions. And let's dig more into details about modules and about services. So actually, we have 3 types of modules. Let's start with the last one, with effector types. So effector types like types of modules that could access file system through WASI. Also, they could call external binaries. The reason why we have such effectors modules and such scheme with 3 types of modules, that effectors is a module that could corrupt your like state, and you want to allow developers to, not developers to like let's call miners, yes, people who could run freelance nodes inside our P2P network just to run safely services by like make some like register of good effector modules, and that identifies by hashes So it's like the same thing as the Apple Store or Google Store or something like this. So let's say factor modules that ones that should be reviewed by someone for doing some malicious things with your file system or some your state. The next type is the pure modules. So it's like is it written? Yes, it's like from functional programming. It's like the modules that can't access file system, or they could access only through effector modules. They could call effector modules and like do only things that they could do. And the last one is a facade. So facade modules expose like API of entire service, and this facade modules could be called from Aqua scripts. Yes, and each service could have only one facade module. And also each service is identified by a special service configuration file. You could see example of already seen example of URL downloader. It consists of 3 modules. And here you can see that each module could have their own settings. For example, you could adjust like WASI settings for modules, saying that, oh, this module's called the local storage could access only files listed in this pre-open files list. And for example, this one Kuro adapter could call some external binary called Kuro by this path. Actually, now we are using CLI interface. And future, when WASI will support Unix socket or socket with support of Unix, socket will also support Unix sockets. So these modules will be loaded by Marine one by one in the sequentially, defined in this configuration file in this sequence. And last one will become facade module. And Marine runtime could be considered like this scheme. Yes. So this Marine runtime allows you to load several services simultaneously, and in its turn, each service consists of several modules. And effector modules, yes, could access file system or call external binaries through WASI. And internally, these modules communicate with each other with help of interface types. And services can't call each other; they are isolated from each other. They have separated memory and so on. It's important that our EAR interpreter. That's why I'm talking about this interpreter on Webassembly meetup. This interpreter written on Rust, and it's also compiled to Webassembly. And it's also compiled to a module that could be loaded inside Marine, inside our runtime. And but this module has some important feature comparing to other services or other modules inside Marine. It could call other services. So it has ability to call other services by special host closure. So let's talk a little bit about Aqua. So just to have some thoughts how it's looks like. And I think that it's better to review several examples. We have more or less complex example of FluentPath. So it's some form of messaging app you can find by this link. And here you can see example of Aqua script. That's our language. We don't have now a highlighting scheme for this language. So that's why just a gist yes, just a text. So here you can see function that allow you to handle user joining. So imagine that we want to write some messenger, yes, and we want to handle when some user is joined inside our P2P messenger. Yes, it's not a centralized, decentralized messenger. And here, to imagine that we have several services inside this, and so this application is identified by special app config. And from this app config, we could find services called user list. So it maintains user list, so list of user. Internally, it consists of SQLite that compile to WebAssembly. Also, like first to be said that we have Redis compiled to WebAssembly that also could be as module inside FC. Yes, should be composed to. So services could consist of like database, not as a separate database, yes, but it's like also compiled to WebAssembly. But let's return back to our script. Here on the third string, you could see that that like operator on, so like on something, we could do this one. So it's like Python-like or identifications here are matters. And here it means that here, please run these two lines on peer ID identified by this string. Yes. So it means that execution flow will be transferred to this peer identified by this peer ID. And on this peer ID, function join will be called. Here, this line, this first line is alias. Yes, just like alias to service ID, this service ID of user list. And this simple function will return join result. So the join result looks like this. Actually, now in interface types and in our SDK, for us, we don't support enum types. We don't, and that's why we don't support result. And so some form of either types, yes. And we now we have a workaround, yes. So we just linearize this either type to this form, and we have some return code, yes, and error message otherwise. Like, but in future, in some point, we will support, of course, enum types and box types, but not now. So here you can see more complex function that operates on two services. So this code intended to handle posting messages. This message is just a string, yes, and it returns some result. It also linearized either type, and internally it does two things. First one, it called history service and adds some entry to the history service, and also then it notifies all users. So here you can see like 4 cycle in parallel. So it notifies all user like in parallel. I describe later what does it mean in parallel. And it will like call special callback, this callback inside browser that like prints this message from the clients. Yes, and here we just so this comparison is needed just to not like to show this message on our client, not to duplicate it. And here you can see that next operator via, yes, it allow you to like move execution to pure ID that, for example, connected via some relay ID to our network. So because like client could be like could not have some wide IP, yes, and it could be like can't be called directly from network. So that's why every like client is identified by relay ID. Also, we have some form of authentication, but I won't cover this in my talk. If you want to, if you want more details, please ask additionally. One last point about Aqua. So it's like its intuition, why it's needed and why like how it's like could help applications. Imagine that we want to do some complex network scenario when we want to go to some gateway and we want to like compose two services, and one service contains database, and in traditional client server workflow, it's will look like this. So we call gateway will like call server will fetch data from database and then return back in response to gateway and then gateway will request another server, and so on. So you could see that there are some additional round trips, for example, this one and this one. Yes, or sorry, this one. And like in peer-to-peer networks, this scenario could be flattened and could be in this form. You can see that this is as optimal as is possible in terms of round trips, in terms of network calls. And with Aqua, it could be like represented in following way. Yes, here you can see just some sequential operators that allows you to transfer execution to gateway, server, database, and another server sequentially, and then return result from the last server. Last slide from this group about Aqua. Actually, we use different technologies for different part of our language stack. So the first thing is the Aqua compiler. It's written on Scala, functional way, and it compiles our like Aqua code. For example, this one, yes, it compiles to our intermediate representation that we'll talk next slide. And then this intermediate representation will be executed inside Marine runtime. Yes, it allows you to execute WebAssembly modules executed by ER interpreter written on Rust and compiled to WebAssembly and loaded inside Marine. So that's how it looks like. So let's move on to Marine intermediate representation and the foundation of it. So actually, as I already said, it's based on pCalculus. And I don't cover all details of pCalculus, but I just want I add this slide to show you some intuition behind several instructions that we have inside here. So the most important thing here is combinators. So here you can see 3 combinators. The first one is so-called sequential combinators. It means that, so first of all, execute P, and if it succeeded, then only then execute Q. This one, third one, yes, is called parallel. It means that please execute P and Q in parallel, and then do something with results. Here, plus means that please execute it's with join behavior. I also won't cover join behavior. What is it? Please ask questions. Next important thing is match and mismatch. So here it's just allow you to branching inside pCalculus, yes, and just compare some values comes from. So here is code process, yes, but by process. So because pCalculus invented in 1980, as far as I remember, and process here could be anything. So it's like I don't know, is like a process as a operation system process, or like another client or something like this. So it's the same thing as a message application could cover many situations inside computer science, because all communication is could be considered as a sending messages. Okay, so and here consists of 8 instructions. Here you can see all of them. So first one and the most important one is a call. Yeah, that allow you to call services, call facade modules of services. Next two allow you to sequentially call or parallel call. It's maps directly to this one. This one fold, it's is like a for it's allow you to iterate through some value. And for example, remember cases when you want to post a message and you need to go through several clients, and this fold allows you to do it. This XOR allows you to catching errors. I will talk a lot about semantic lately, but it's only a brief overview of it. Next two is match and mismatch. I think they obvious. They just transfer execution if values matched and mismatched. And now is empty instructions that allow you to generate code, and inside like it's a generator, you need to generate some instruction that does nothing. So on this instruction code now, exactly in this P calculus. So let's see what each instruction do internally, and start with call. So call is the most important instruction and is one of the most complex. Here semantic is also complex. So call allow you to call some service on peer ID identified by this like peer ID. So the first argument of call, and then call service identified by the string and function like so identified by this like third parameter, and call this like function of service located on peer ID by this arguments, and set result to some value. Is it here is the last one. Next one is a Sequ. Yes, Sequ allow you to, so it takes two instructions. They could be not only call, yes, they could be like several instructions. That could be another Sequ, and so on. So I call it, we call it subgraph or subtree. So sequentially allows says interpreter to call to execute these instructions sequentially. What does it mean sequentially? I will cover later. In parallel, do a similar thing, but in parallel. Parallel is a complex thing, and it's not means that you need to execute on one peer in parallel, like in multi-threading, all executes in one thread, but in terms of network, it called in parallel. XOR one also takes two instructions, and it executes the first one, is first subgraph or first subtree. Yes, and if some instruction inside this subtree failed, and only in this case, it called next subtree. So I will call this first one left subtree, and next one right subtree. And yes, it's like first instruction, left subtree fails, then only then it will call right subtree. Last one is a float, is also complex instruction. It takes iterable, yes, it's like array that it iterates on. Then it's assigns each value to some iterator. Yes, and then you could use this iterator inside subtree. This subtree, I mean, this also instruction is also subtree. So here you could see example of how like complex script could look like. Here you could see like fold that call sequentially some. So this one is like iterator, so it's like array-like structure, and here is iterator. Yes, this iterator could be also we support JSON pass. So this one is JSON pass, and from this value, we, for example, it looks like this. Yes, it's like users is arrays of some objects in terms of JSON. Yes, JSON object that have, for example, peer ID field. Here we could obtain this peer ID field by this JSON pass and call and use this like obtained value as a first instruction of call. And this one next that won't cover it on the slide with all instructions is like another one. Yes, ninth one, if it could be say. It's like iterates through users and set iterator to next value, and this next could be placed anywhere inside fold. For example, if it could be placed here, this fold is a left fold. It's like moved value from handle value from left to right. If it would be here as the first, so imagine that here first next and like second one, so right after is a call. And in this case, this fold became a air fold, yes, like from, I don't know, from Scala or other functional languages. And it will start from very end of the array and handle elements from right to left. Okay, and house construction is a very simple one, is a null, so it doesn't take any arguments, it's just a null. So it does nothing. It really does nothing. Okay, and the last thing that is important for our network is a particle. So particle is some form of data. So it's particle is a piece of data that transfer between peers. For example, if we consider this the script, you could see that here are several calls, and each call change data. I will cover data later, what is data is, but data is like a execution sequence or state of interpreter, and it's like call several nodes, and when each node is called, the execution transfer to this node, to this peer ID, is identified by this variable. And all set data before you transfer to this node in form of particle. So particle contains script data and some other metadata that needed for a node. But for interpreter, it's matters that particle consists of script data and the init peer ID. Init peer ID is a peer ID of client who initiates the script. So let's consider the last section is implementation of interpreter, and also remember the general scheme. Here, like FC is a marine, yes, and it's like all stack looks like this. Yes, we have peers that run services inside WebAssembly with help of interface types, and execution flow transfers from one peers to other with help of Aqua stack. Yes, with so Aqua plus Aquamarine intermediate representation. So it's like it's layer of choreography or network management. Yes, and this one is layer of execution inside FC. So from some formal point of view, or like math point of view, so our interpreter could be considered as a state transition function. So it's like a state machine. Yes, in its take data from particles that comes to node, and it's also previous data if it was on node. Yes, for example, particle could particle is like particle for one script. It could come to one node several times, and like from previous times, there would be previous data, and like data from new, like the new coming case, and from previous coming come from our interpreter, and our interpreter produce two things. First thing is a new data that would become previous data on the next round, and a list of peers or list of peer IDs or public keys that this new data should be sent. So it's like it's very simple. So it's like a black box that produce you a data that you need to send to peers from this list, and it's like all inside WebAssembly. But this interpreter isn't a pure function. So because internally it calls services located on node and some built-in functions. Some built-in functions allow you to discover some peers, resolve topology, and so on. We have like documentations about this built-in function, so that they are not services inside WebAssembly, but they special function inside our node. They mostly intended for some network management. And here you could see how it looks like from Rust, and from how it could be, how it's implemented. So like this function invoke is also run by FC. So here I need to say some additional information. Actually, we run interpreter both server side, both inside our node and both in client browser. And we have two building targets. one. So this invoke function is the same for this build targets, but for clients, it's wrapped by Webassembly engine. Yes, and for server side, it's wrapped by FC. But internally, it's almost the same, except this moment. And this invoke function receives init per ID from particle, Aqua script, previous data, and data that I will call current data, and produce new data. Because we don't support result as either types, the return structures looks like this. Yes, it will. So the important fields here is the new data. This one, this is it, new data, and the new it's list of peer IDs or public keys of peer IDs that data should be sent. This new data. Inside interpreter, we have values that could be two types. First type is a very simple with the scalar values. Actually, inside interpreter now, all values except streams are JSON-like. So it's from Serdeo, because we now on prototype we decided to use JSON. In the future, we would switch to interface types, and all values would become interface types like. I mean that there would be seamless integration with Marine, but now it's JSON, and they are fully consistent. I mean that they are not CRDT-like; they are the same on each peer, and they could be arguments of any instructions, that any of 8 instructions, match, call, and so on. Streams are much harder to understand. They are CRDT-like, but by CRDT-like here means that they could be differ on different peers, but they have a property that they append only, and the beginning of, so that the left side of the stream always the same for one peer. That's why they are functional data type. They have versions. They they could be clinicalized. By clinicalization here, I mean that they could be. I think that it could be say that it's could be switched to scalar values. So it means that Aqua could say, so now on this this stream could be fixed on some peer. So the state that differs in different peer, but we want to fix it on this peer and say label something somehow. Sorry, and without clinicalization, it could be used only inside fault, only by iterable fault. And in the moment, it's only partially implemented, and now streams. Not CRDT-like, they could be different execution, but it's very hard to obtain the situation. We are working to make it CRDT-like in this following way. And from code point of view, they look like this. They prefix it with $sign, and the difference here is that you could add to end of the stream some values, because to scalar values could be assigned only once during script execution. So how interpreter works internally? Actually, it treats instruction as a graph, as I already said. For example, imagine this simple script with 3 instructions, and actually is a graph. Yes, but it's it could be said that actually is a tree, because fault could be. So this you could see how code could be represented as a graph, and fault here also. Here you could see that next here is a cycle. Yes, because next call fault again, and also it's important that there could be several nexts inside one fault. But actually, you could say that this one could be I don't know. Could be replaced by all nodes inside this fault tree. Okay, And from code point of view, it looks like a visitor pattern. Yes, it's have a trait executable instruction that implemented for all instructions, and they I have two context, execution context and trace context. And the other important thing that it's like we do not have any entry point. So entry point is always the same, is the root of graph, whole graph. And each time execution starts from the very beginning of script. And so this one is needed to check proofs of that previous instruction was called, really called. Because now we don't have such a feature, but in future, each node would sign like the result that they placed inside data. I mean, the interpreter inside node will sign by PID public key, by private key, will sign the result, and before execution, each node would check these results. Like to also, it's we don't want to execute same calls several times, and to avoid this, we invented like algorithm of linearization of this tree, and so data that like was like current data, previous data, and new data actually is just this one is the execution trace that consists of just arrays of executed states. That in each executed state is a enum, yes, with three instructions, par, call, and fold. And here you can see that how it looks like for call and par. So par here is just the two values and size of left subgraph and right subgraph. Why it needed, I will show you later. So that's why, like during execution of instruction, interpreter looks at data. So was it already executed? Yes, it's identified by this enum variant. If so, it won't be executed again. So this is how main like execution function looks like. It does three things. First one is like prepare context. Internally, it merge previous data and current data. Yes, I mean, this one, it's merge it like as the first step. And then it executes script and the pack result. So the last step. Here you can see how merging could be done. So like our execution graph is linearized to a trace. And imagine that like previous data was in following form and current data would be following form. Here you can see that like subtree of pairs could be differ, and they identified by size of subtree. And while merging, here we just this like imagine that this go from a right subtree, and this will be placed after left subtree. And also there are other other situation. It's the most simple one, but I think it's too hard to like talk about it. It's like on this slides, because it's really hard to like it's really hard to understand probably. But so it's like the possible way how merging process could look like. Okay, so and we talk about how call executed, but also in general, interpreter tries to like execute all instructions, so cover all, in other words, cover all like nodes and our graphs. Yes, and internally tries to execute all calls. But like execution rules are different for different instructions. And for example, like SQL has rules that like right subtree or right subgraph, yes, of SQL could be executed only if left was completed. Like it means that all calls inside left subgraph was executed. For XOR, rules are different. So it means that so here, sorry, there is a sub-tree and subgraph, but it should be like it's inconsistent. So here, imagine it's like subgraph. So where right subgraph of XOR executed only if on the left subgraph some instruction failed with a error. So it's like a form of catch. And parallel, what does it mean by here by parallel that I wanted to talk about? So here it means that override sub-tree view executed if left doesn't fail. So it means that compared to sequential execution, right subgraph or sub-tree, again, it doesn't matter, you executed with left, yes. But the only thing that will break these processes if some call on the left or some instruction on the left sub-tree was failed, and then my fail will bubble it up to the next XOR instruction. So here is how call is executed. Actually, there are two situations when. So also remember how call looks like. Here is the first argument is a pure ID of a node or peer. It's a network that we want to call this service with this function. There are two situations when pure ID is equal to current node peer ID, where interpreter is 1. And if it is, then it executed synchronously. I mean that like it executed on this like node synchronously. If it's not equal, then this pure ID will add to next pure ID that will return by the interpreter. So, and like one of the last slides, we have, of course, we implemented most of the things that we wanted, but also we need to implement dozens of other things. And as already said, we do not have caching and signing of results. Also, we are using JSON. We want to switch to interface types. Our ear doesn't have binary representation now. We are working on it either, and getting also JSON path was our the most huge feature, because JSON path is really very thin. There is no any specification of JSON paths, no good libraries, so it's mess. Yes, actually, and you want to get rid and use some interface types like accessors. And also we want to implement Academia routing as an Aqua library, and some other things. This is, so actually there are a lot of them. So like today, I hope that I review most of the things that we are using Aqua Stack. All of them are open source. You can find them by these links. So I was covered Marine virtual machine or runtime. So we haven't renamed it yet. Rust SDK, Common Intermediate Representation, and Aqua. So if you have any questions and if you are interested in these technologies, please follow us on Twitter. You could subscribe our newsletter on our site, and you could reach me by this email or by this Telegram link. So thank you all. Thank you, Jonathan. So that's it.
Awesome. Well, thanks for sharing all about Aqua Marine and all the cool stuff you're working on at Fluence, and staying up super early or super late, depending on how your clock works. So extra round of applause for Mike for delivering that talk. We are basically over time, so which is great. Lots of stuff. It sounds like you could have gone on for even more, but we'll flip over to the Discord. We'll end the live stream and look forward to seeing many of you in a future WebAssembly virtual event. And thanks for staying up. Thanks for hanging out, and talk to y'all soon. Take care. Bye.
Thank you.
Thanks, Jonathan.
Thanks.